Hello students, welcome to the last set of examples of the shear force diagram and the bending moment diagrams. We have already explored a centrally concentrated load, a simply supported beam, then a uniformly distributed load onto a simply supported beam, a concentrated couple on a simply supported beam, a concentrated force and a concentrated moment on cantilever beams, and a combination of concentrated force and a concentrated couple on a simply supported beam. Now, just to have the loading configurations a little bit complicated and to understand how we are going to tackle it to draw the bending moment and shear force diagram, a problem has been chosen from the reference where a triangularly distributed load from the left end of a simply supported but with overhang a beam is gradually increased and then stabilized with a uniformly distributed load till it's some length of the span, and then there is a concentrated force at the overhang portion, tip of the overhang portion. To draw, and you need to draw the bending moment and shear force diagram for this particular beam with the loading configurations. How to proceed? First of all, you should draw the free body diagram of this. I have not drawn that. I have extracted it from the textbook and finding out the reactions at 1.233 kilonewton on the left side, and R2 is 3.27 kilonewton here at the support where it is supported on a roller joint. Now, to deal with this, finding out the reaction, for that, what you need to do, you need to find out the CG of this triangular loading, which is very easy. It is actually 2/3 from the left end of this triangle. And then the CG of the center of gravity of this loading, which is uniformly distributed over 2 meters, is just in the middle, 1 meter from this end, 1 meter from this end. So you can easily find out the reaction. After find the reaction, you need to consider sections onto the beam at locations which are characteristically reflecting the same type of loading. So you take a section at a distance x1 to tackle the triangular load. So you will extend the x1 distance from 0 to 2 meter from the left end. Then you take a section at a distance x2 and extend x2 from 2 meter to 4 meter, and then take a section x3 which will be from actually 2 plus 2 4 meter to another 1 meter, that means 5 meter, 4 to 5 meters. And then the last 1 meter, it will not be convenient for you to take sections from the left end. You will take from right end and quickly find out the shear force and the bending moment diagram. See that? So I have not completed this particular problem that you have to do because you have got now the enough evidence that it is that easy. So you take a section at x1, and then from this triangle with a length of x1 on the beam length, you can find out how much it is loaded. You assume the shear force and the bending moment acting over the cross section of the beam, apply the equilibrium equation, have the equations of shear force and moment by taking a moment here and considering all the vertical forces 0, and then keep on writing that. And the next time when you come, you include the total triangular section as well as the part of the uniformly distributed load which is at a distance x2. So x2 is basically x1. You can say that this is actually 2 meters. So 2 meters is the extent of the triangular diagram, and x2 minus 2 is the extent of this uniformly distributed load. So the CG of the loading will be situated at x2 minus 2 divided by 2 from the section. The section is cut here. So the vertical shear force downward is V2, and an anti-clockwise moment M2 will act here. Similarly, if you take a section from the right side at x3 from left side or x3 from right side. If it is x3 from right side, I have indicated it otherwise, but if you take it from the right side, it will be convenient for you because you know this is actually 1 meter. The total is 6 meters. So anyway, if you take from left side, it is 6 meter minus x3 is this length. This is actually taken from left side, but you could have taken from right side. So 6 minus x3, and this you can easily find out what is the length, because this is 1 meter. So this is totally 1 meter. So now, actually that this is, the x3 should extend from here, not from the support. Let's please make a correction here. I'll make a correction later. So anyway, it is at x3 distance, so 6 minus x3. Now you can have you can examine carefully the actually the shear forces and bending moment. Please examine that the shear force is not linear for certain cases. When the loading intensity is actually uniform, the shear force is linearly varying. When the loading intensity is varying, the shear force is non-linearly varying parabolically. And when the loading is absent, you have a constant shear force without change. And if you consider from the right part, the 1.5 is right down. You have considered left up, right down. So this is the positive shear 1.5. You see, I've forgotten the positive sign, but I have drawn it correctly onto the positive side 1.5. Like that, it will be possible for you to complete the shear force and bending moment diagram for this particular figure. So I assign it to you homework for you to try it yourself, because it takes a long time in the video to explain, but it is easy to do it for yourself. So once again, it's a combination of uniformly distributed, linearly varying load also, and a concentrated force acting on an overhang simply supported beam. And we are after the shear force and bending moment diagram, and here is the variation. Just to convince you it is correct, at least at parts, you consider the right part, you have a 1.5 force, left up, right down shear, you have a positive shear. Similarly, your bending moment, it is the anti-clockwise moment which should have been positive, but this 1.5 force is creating about this point a moment. 1.5 into 1 meter is a moment 1.5 kilonewton meter, but that is negative, and that is how it is a negative bending moment up to here where the support R2 is situated. You do it and complete it the other parts. Let us move to the next example. This is somewhat a offbeat example. It may not appear in the examination, but for the completeness, it is actually explained. You will get a plenty of examples where there are cantilever beams are supported at the end, but to release the moment, there is an internal hinge mechanism is created. There is no harm, it will not fall down. The structure is well fixed at the left end as a cantilever beam, so there is no chance that it will be suffering any stability. So now the thing is that it is loaded with 800 Newton and a 200 Newton meter actually end moment, or the couple applied at the end at the joint, where onto the member. This couple is applied onto the member, not onto this roller joint. It is onto the member. Sometimes from the book we are confused. This type of end moments, you may ask yourself, how come a moment exists at the roller joint? Because we have learned that moment is released at roller joint. Yes, this is released, but you are applying a moment onto the member. Suppose with a pin you are trying to bend the member with a moment, that you can do, but otherwise there is no moment possible here into this joint. So no moment will be transferred to create a moment here, but you can apply a moment separately. How to deal with this problem? Internal hinges, you observe your umbrella, the sticks inside, so they are with hinge joint. Your hand is you have at your elbow, you have a hinge joint. So that hinges releases moment. It does not resist the moment, but it releases the moment, but it resists here. So there is a shear force reaction if you separate the structure. The moment you see an internal hinge, please separate the structures into two parts, and you will have a shear force and not any moment. So you have to now solve an equilibrium problem first and find out the reactive forces, which should be now easy for you after so much of discussion. If you sort out the free body diagram for both the parts separately, you can explore how to draw the shear force diagram separately. In fact, this part will more or less look like your first problem, where you have a central concentrated load, but mind that the reactions are different because there's a moment working at the end due to the fixed support, and you have a difference into the shear force diagram, not the same magnitude both sides. So I hope that you will not face any problem in drawing this diagram here. And since the hinge joint, ultimately the moment is to be 0 here, because there is no external couple applied at this position. So the moment is 0 here. You try it yourself, and then we will explore more. I think this is the end of the example, and now we should explore the axial force, and the twisting moment diagram.